The normal distributions by Professor Frey. All normal distributions have the same general shape. They're single-peaked and symmetric about the mean. Normal distributions are described by two parameters, the mean mu, which again is the center of the distribution, and the standard deviation sigma, which affects the spread of the distribution. So notice as we change the mean, the center of the distribution shifts, but the overall shape is the same for the same values of sigma. So standard deviation gets smaller, the spread of the distribution gets smaller, and as we increase the standard deviation, the spread of the distribution gets larger. Larger standard deviation, more spread. The 68, 95, 99.7 rule. For a normal distribution, we know that 68% of the scores lie within one standard deviation of the mean, 95% lie within two standard deviations of the mean, and 99.7% lie within three standard deviations from the mean. So knowing the mean and the standard deviation really gives you a lot of information about the distribution. Remember, the mean is the center, and if we have the standard deviation, we have a pretty good idea of how the data is spread out. 68% within one standard deviation, 95% within two, and 99.7% of the distribution is within three standard deviations of the mean. So let's see an example using that. Heights of adult females are approximately normally distributed with mean of 65 inches, so that's 6'5", and standard deviation of 2.5 inches. So given that information and the 68, 95, 99.7 rule, we know that 68% of adult females are between 62.5 and 67.5 inches tall. We know that 95% of adult females are between 60 and 70 inches tall. And we know 99.7% of all adult females are between 57.5 and 72.5 inches tall. The standard normal distribution. All normal distributions have the same shape if we measure in units of size sigma about the mean mu. In other words, measuring how many standard deviations a score is above or below the mean. Changing these units is called standardizing. If an observation x comes from a distribution that has mean mu and standard deviation sigma, the standardized value is z equals x minus mu over sigma. We find the difference from the score to the mean and then divide by the standard deviation. A standardized value is often called a z-score. The standard normal distribution then is a normal distribution. This notation gives us the mean and the standard deviation. So it's a normal distribution with mean 0 and standard deviation 1. If we have a variable x that has a normal distribution with mean mu and standard deviation sigma, then the standardized variable, z equals x minus mu over sigma, has the standard normal distribution. So we can turn any normal distribution into the standard normal distribution by standardizing the scores. Let's take a look at some examples. IQ scores are approximately normally distributed with mean of 100 and standard deviation of 15. We're interested in finding out what is the probability that a randomly selected individual has an IQ score below 120. The first thing I tell students always to do is draw a picture. So here's the picture. We've got a normal distribution with mean of 100. We're interested in looking at the values that are below 120. So 120 is about here, and we'll shade the region below 120. The next thing you want to do is calculate the z-score. So that's x minus mu over sigma. X is 120. The mean mu is 100, and the standard deviation is 15. So the z-score is 1.33. When you calculate z-scores, always calculate to 2 decimal places, because that is the number of decimal places that we find on our standard normal table. The next thing we want to do is look that value up on the table. So here we have our table of standard normal probabilities for positive z-scores. You can find these online, and probably you have one in the back of your textbook. And we're looking for a z-score of 1.33. So here's how this works. You look for 1.3 in the first column, and then we want 1.33, so we're going to look for the 0.03 column. And then we want the intersection of those two, and the area is 0.9082. So that's the area under the curve less than a z-score of 1.33, as shaded in the picture above. So we find that the probability x is less than 120 is the same as the probability that z is less than 1.33. That corresponds to the area under the curve that we just found, 0.9082. So about 91% of the individuals would have IQ score less than 120. Here's another example with IQ scores. Here we want to know the probability a randomly selected individual has an IQ between 70 and 120. Again, the first thing you want to do is draw a picture. And here we want to find the area under the curve between 70 and 120. So we're going to calculate two z-scores, the one corresponding to 70 and the one corresponding to 120. And we've got those there. So this corresponds to a z of -2. When we look up the area under the curve in the standard normal table here, we're going to find this area of this little white tail. When we look up 1.33, and we've already done that, that's the area below 120, so it includes that tail. So to find the shaded region, what we're going to do is take the difference of the two. The area less than 1.33 minus the area less than a z-score of -2. Okay, so let's go to the normal tables now. So we've already looked up the z-score of 1.33. Now we're interested in looking up the area below a z-score of -2. So now I'm looking at the standard normal for negative z-scores, which is the previous page, and I'm looking for -2.00. So I'm going to go down this column until I get to -2, and since the hundredths digit is 0, I'm looking at the first column. So I see the area is 0.0228. So the probability that an IQ score is between 70 and 120 is going to be the area corresponding to a z-score of 1.33, which we already looked up was 0.9082, minus the area in this little tail region, which was 0.0228. So the final answer is 0.8854. So about 88.5% of IQ scores are between 70 and 120. Another example with IQ scores. What's the probability a randomly selected individual has an IQ score above 130? So again, we'll draw a picture. Here's an IQ score of 130. Again, the mean is in the middle, 100. And now we want the probability the individual is greater than 130. So when we calculate the z-score that corresponds to 130 and look up the area in the table, we're going to find the area of this white region here below 130. If we want to find this region, we need to use the fact that the total area under the curve for any probability distribution is 1. So when we find this area, we're going to subtract that value from 1 to get the area of the small shaded region. Again, we'll calculate the z-score for 130, which is 2. And if we look 2 up in the normal table, now we're looking for a z-score of 2.00. So again, I'm in the table for positive z-scores, and I'm going to look for 2.0 in the first column. And so since the hundredths digit is 0 as well, I'm looking in the first column, and I see an area of 0.9772. So that's the area below a z-score of 2.0, 0.9772. When we look -2 up in the normal table, we found an area of 0.9772. So we're going to subtract that from 1, and we see a value of 0.0228. So about 2.25% of the area is in this table. Remember, we saw this value a minute ago for the area below -2, and it should make sense the normal distribution is completely symmetric. The area below a z-score of -2 is going to be the same as the area above a z-score of +2. Well, now I want to calculate the 75th percentile for IQ. Now remind yourself what the 75th percentile is. That's the score that separates the bottom 75% from the top 25%. So we want this total area under this score that we're trying to find to be equal to 0.7500. Now what we need to do is look in the standard normal table and try to find an area of 0.75 and work backwards to find the z-score that corresponds to that. To find the 75th percentile, this time what I'm doing is I'm looking in the areas in the body of the table, and I'm looking for the value closest to 0.7500. So I want the 75th percentile. So what I do, go down the first column of areas, the second column of the table, and follow down until you see the last number less than 0.75. You see 0.7580, that's bigger than we want. So I see 0.7257. What I'm going to do then is go across that row until I find the value that is closest to 0.7500. Notice 0.7500 is between these two values, 0.7486 and 7517. 0.7486 is closer to 0.7500. So I'm going to pick that one. Now what I want to do is figure out what's the corresponding z-score. So if I hold my place there and go across, I see that the z-score is going to be 0.6. And if I go up to the top of the column, 7. So 0.67 is the z-score we want for the 75th percentile. 0.67. We're going to use a z-score of 0.67 to correspond to the area of 0.7500, because that was the closest one we found. And now we want to solve for x. So that z is x minus mu, which is 100, over sigma, which is 15. And we just want to solve for x. So we're going to multiply by 15 on both sides, add 100 to both sides, and it turns out that x is approximately 110. So 110 would be the IQ that corresponds to the 75th percentile. So I hope that helped, and have a great day.